You know, every single second, our sun unleashes an absolutely staggering amount of energy. I mean, more than humanity has used in its entire history. It's this colossal nuclear furnace just hanging out in our sky. But, like all stars, it's not going to last forever. And that really makes you wonder about its final moments, doesn't it? What is our star's explosive secret?
It's really the ultimate question for our little corner of the cosmos. We see these incredible pictures of other stars ripping themselves apart in these cataclysmic explosions, supernovae, that can literally outshine their entire galaxies. So is that the spectacular fate waiting for our own sun?
All right, let's just get right to it. The short answer, and thankfully for all of us, is a solid no. Our sun will not, and in fact, it cannot, explode in a supernova.
But that simple no is really where the fascinating part of the story begins. See, the reason why our sun is safe from that fiery end uncovers the fundamental rules that govern, well, the lives and deaths of every single star in the universe. It's a story about a cosmic balancing act, about mass, and about two very, very different destinies. So, to get why, first we've got to look at a star's balancing act. For most of its life, a star is in this state of perfect, delicate equilibrium. It's a constant, high-stakes cosmic tug-of-war going on inside. This amazing balance is called hydrostatic equilibrium. On one side, you have the immense, relentless force of the star's own gravity, just trying to crush it all down into a tiny little point. But fighting back from the core is the unbelievable outward push from nuclear fusion. And for billions of years, these two forces are just locked in a perfect stalemate. That's what keeps a star like our sun stable.
Okay, so if all stars have this internal battle going on, what makes their endings so different? Well, it all boils down to one single crucial factor that's decided the moment a star is born: its mass. For a star, mass isn't just a number, it is its destiny.
And this right here, this is the magic number, the critical threshold: 8 solar masses. A solar mass is just the mass of our sun, so we're talking 8 times heavier than our star. Any star born with less than that follows one path. But any star born with more, well, it's destined for a much, much more violent end. This is the great dividing line in the cosmos. Let's just compare these two paths, side by side. Our sun, that's a low-mass star. It's going to live a long, stable life for billions more years. And then it'll gently puff away its outer layers, leaving behind a quiet little remnant called a white dwarf. But those high-mass stars? Oh, they live fast and die young. They burn through their fuel in just millions of years, before ending in a catastrophic supernova, leaving behind either an ultra-dense neutron star or, sometimes, even a black hole. So let's bring it back home, to our own cosmic backyard. We know the sun isn't massive enough for a supernova, so what is its gentle end gonna look like? Well, we actually have a pretty clear forecast for what's coming.
It's a whole process, not a sudden bang. First, in about 5 billion years, the hydrogen fuel in its core is going to start running low. Without that outward push, the core contracts and heats up, causing the sun's outer layers to swell up, just dramatically, into a red giant. It'll get big enough to completely swallow Mercury and Venus. After that phase, it'll shed all those outer layers, creating a beautiful, glowing cloud called a planetary nebula. And finally, the core that's left over will collapse into its final form.
And that final form is a white dwarf. This is how it ends for stars like our sun. You get an object about the size of Earth, but it still has about half the sun's original mass packed inside, making it unbelievably dense. A single teaspoon of white dwarf stuff would weigh tons here on Earth. It's not making any new heat, it's just a cooling stellar ember destined to slowly fade away over trillions of years. A quiet, peaceful end.
So, if that's the gentle path, what does the violent one look like? Okay, now we get to the main event, the core collapse supernova. This is what happens to those monster stars, the ones born with more than 8 times the sun's mass.
You see, inside one of these stellar behemoths, the core isn't just one big furnace. It's actually layered, kind of like an onion. As it gets older, it fuses hydrogen into helium, then that helium into carbon, and so on, creating these shells of heavier and heavier elements, all the way down to iron right at the very center. And this is where things get just incredibly dramatic. Just look at this time scale. A massive star spends millions of years fusing hydrogen, another million on helium. But the final stages, they are shockingly fast.
It burns through all of its carbon in about 1,000 years, and its final fuel, silicon, lasts for just about 5 days. The star is in this frantic race against its own collapse. The beginning of the end comes when that iron core grows to about 1.4 times the mass of our Sun. This is a famous threshold in physics called the Chandrasekhar limit. Up to this point, the core has been propped up by something called electron degeneracy pressure, which is basically just electrons being squeezed so tightly together they physically can't be squeezed any further. But at 1.4 solar masses, even that incredible pressure fails. Gravity wins, and it wins decisively. There's absolutely nothing left to stop a catastrophic collapse.
And that collapse is almost instantaneous and just unbelievably violent. The core implodes on itself, reaching speeds of up to 23% the speed of light. We're talking 70,000 kilometers per second. The temperature spikes to 100 billion degrees. All that infalling material then crashes into this now ultra-dense core and rebounds, creating a titanic shockwave that just blasts the rest of the star apart in that glorious explosion we call a supernova.
But here is the most beautiful part of this entire violent story. This spectacular act of destruction is also the universe's ultimate act of creation. A star's death is, truly, the beginning of new life.
You see, that shockwave we were just talking about, it's so energetic that it triggers one final, fleeting moment of fusion. This is the only way the universe can create elements heavier than iron, things like gold, platinum, uranium. And the supernova doesn't just create these elements, it blasts them across the galaxy, seeding these giant clouds of gas and dust with the raw materials for the next generation of stars, planets, and, well, us.
What this means is that every heavy element that makes up our planet and even our own bodies was forged in the heart of a massive star and then scattered by its explosive death. The iron in your blood, the calcium in your bones, we are, quite literally, made of stardust. The death of ancient stars was the necessary ingredient for our existence.
And that leaves us with a final, pretty humbling thought. Our sun won't go supernova, but it will still enrich the cosmos when it dies, creating its beautiful planetary nebula and leaving behind that white dwarf core. So, if we are the legacy of stars that died billions of years ago, what incredible things billions of years from now will be made from the remnants of our own star?